In this video, we're going to look at the chain rule. The chain rule is a technique used for differentiating composite functions or functions of a function. Let's just recap what a function of a function is. If we take now one function of x, and let's say that's the f of x, and we had now the f of x was a linear function 2x plus 1, and we had now another function of x, let's say the g of x, and the g of x was x to the power 50, and then we had a third function, and we could call that h, and this was now e to the x. We could look at building a range of different functions. So we could have the g of f of x, the f of g of x, h of g of x, h of f of x, or for example, the f of g of h of x. We've looked at a video on creating these composite functions. So let's look at one in particular. Let's say we've got now the f of h of x. We would do h, then we would do f. So h is e to the x, f is 2x plus 1, so we'd now simply insert e to the x in every time we saw an x. So the f of h of x, as we do h first, then f, so we'd have now 2 lots of e to the x plus 1. If we wanted the h of f of x, then we would now do f first and then h. So we would take f and sub it in here. So we'd have now e to the power of 2x plus 1. So they are two examples of functions, or composite functions. So where does this fit in to the chain rule and work that we've done in the past? Let's take an example now, and we had, let's say we've got y is equal now to 2x plus 1 all squared. And we wanted to find dy by dx, the gradient function. So we wanted to differentiate this. The technique that we would have used in the past now was to expand this out. So we could say y would be equal to 4x squared plus 4x plus 1, and then we would simply differentiate. We'd multiply down by the power and drop the power by 1. So we'd end up with now dy by dx would be 8x plus 4, and that would be the derivative. And that was fairly straightforward. So I've expanded now 2x plus 1 all squared, and we've gone ahead and just differentiated term by term. Now what if that was 2x plus 1 all cubed? 2x plus 1 now to the power 4, to the power 5, right the way up. Now it's quite clear that the higher that power, the more algebra we're going to have to do. We could of course use the binomial expansion, but we can see if I've got now to the power of 3, I'm going to have 4 terms. If I have to the power 4, I've got 5 terms. So I'm always going to have a large number of terms. There must be some better way of differentiating what is essentially a function of a function. And that's where the chain rule comes in. So let's have a look here. We could go ahead now and make a particular function right here. So let's say we were looking now at the g of f of x. So if I'm doing the g of f of x, I take f first and then it goes into g. So this now gives me 2x plus 1 to the power of 50. Now let's just call this y. Let's say y is equal now to this function of a function, and I want to find the derivative dy by dx. Quite clearly, I'm not going to use now binomial expansion to expand this out and do it term by term. As cool and as interesting as maths is, I don't want to go through that rigmarole, and certainly if that's to the power of 100, or if we have, for example, a negative fractional power. So for example, now if I had y is equal to the quantity 2x plus 1 to the minus 2/3, in terms of a binomial expansion, it would be a complete nightmare. So that's where the chain rule comes in. If we have a function of a function, we can introduce a new variable. Usually that's u. Sometimes we use t, but in general we will have u. So what we're going to do then is in this particular case, we're going to take now u, we're going to let u be equal now to the inside function. And when I'm talking about the inside function, in this particular case, we're talking about the f of x. So we let u be equal to 2x plus 1, where u is a function of x, and we can differentiate this with respect to x. We can say, therefore now, y will be equal to u to the power of 50. So all I've done is said now that if u is equal to 2x plus 1, then y is equal to u to the 50th. We create what we call a chain, and we use the chain rule. We can say now that dy by dx will be equal to dy by du multiplied by du by dx. So what we're looking at here now is differentiating y with respect to u and multiplying it by the derivative of u with respect to x. And as you can see, they are fairly straightforward derivatives. This is called the chain rule. Essentially what we see now is that these du's cancel. And whilst we treat them like fractions, they're not actually fractions, although we can, for this purpose, see them as fractions. They are what we call limits of fractions. And if you look back at what delta y over delta u is, that would be a fraction, but these are the limits. But we can essentially treat them in that way. So dy by dx is dy by du multiplied by du dx. As you will see over time, this is really quite mechanical and it's a fairly straightforward process that you can do mentally with a little practice. So let's go ahead now and look at this. So what I want then is dy by dx. Let's first look at dy by du. So we can say that dy by dx is going to be equal to dy by du. So dy by du is going to be multiplying down by the power and dropping the power by 1. We're going to have now 50 u to the power of 49 multiplied by the derivative of u with respect to x, which is just going to be 2. So all I've done then is written that dy by du will be equal now to 50 u to the power of 49. We've got du by dx will be equal now to 2. I'm going to multiply these and then substitute back in. So what we end up with then is dy by dx. So we've got now the derivative of y with respect to x. So we're back to our original function, y in terms of x. And that's going to give me now 100 u to the power 49. We can say, but u is equal to 2x plus 1. So all I'm going to do is simply sub that in. So what we've got now is dy by dx will be equal to 100, and then we'll have the quantity 2x plus 1 to the power of 49. If you want a very mechanical way of thinking about this, we differentiate the outside function, we leave the inside function alone and multiply through by the derivative of the inside function. So let's run through that algorithm again. We differentiate the outside function, we rewrite the inside function and multiply through by the derivative of the inside function. That's often easier to see if we're using function notation. So let's say we want now the derivative. Let's write it here. Let's say we want the derivative, so the derivative with respect to x now of the composite function, and we had now f of g of x. We could write this now as f dashed, and then what we're going to have now is g of x, and then we're going to multiply this by g dashed of x. Often this is a more intuitive way to think about the mechanical process, but often seeing this particular notation allows us to think about these du's cancelling, for want of a better description. So if we've got now a composite function, so in this particular case we have the g of f of x, I've just done the f of g of x, it really doesn't matter. What we do is differentiate the outside function. So the outside function in this particular case is f. We rewrite the inside function, which is g of x, and multiply through by the derivative of the inside function. So f dashed of g of x multiplied by g dash of x. It's less likely you'll see this notation, but in terms of the algorithm, it's a lot easier to get your head around. Alternatively, you could look at it like so. Now, I've built up the chain by having these two particular values here, if you like. We could build this further. We could have another one. So, for example, if we wanted to go from dy by dx via another variable, we could do. So let's look at another example of one that I've just done, and we'll go through the formal process, and then we will look at a very algorithmic way or a mental way that you could do this. So let's say we had now y is equal to, and we'll have, let's go for 3x minus 4, and we'll take this to the power of 1/2. So we say now let u be equal to the inside function, which is 3x minus 4. Therefore, what we have now is that y is equal to u to the power of 1/2. So what we want then is dy by dx. dy by dx is the first derivative. It's differentiating y with respect to x, or the gradient function. We have now the derivative of y with respect to u multiplied by the derivative of u with respect to x. So let's now find dy by du. So we can say that dy by dx will be equal to dy by du. And I'll just write it here. Let's put dy by du. So all I'm doing now is differentiating this algebraic expression or algebraic term. So we multiply down by the power, we rewrite, or drop the, let's just say drop the power by 1. We rewrite now this function right here and drop the power by 1. So we can say that dy by du is going to be now 1/2 u to the power of minus 1/2. And then we multiply through by the derivative of u with respect to x. So du by dx is simply going to be 3. Now it's going to be 3 because that's a linear function. If it was 3x squared minus 4x, then we would differentiate the polynomial in the way that we've looked at differentiating term by term before. So all we do is multiply by 3. So we have now that dy by dx in terms of u will be 3, and then I'm going to write this now as, we've got now u to the minus 1/2. We could write this as 3/2 root u. It's entirely up to you on how you want to show that. U to the minus 1/2 is 1/root u. But we know that u is equal to 3x minus 4, so we can say, but now u is equal to 3x minus 4. Therefore, we can now say that the derivative dy by dx, and just writing this out, so dy by dx is going to be equal now to, we're going to have 3/2 lots of the square root of 3x minus 4. Alternatively, if you wanted to do that mentally, you could do. So what we do now is we differentiate the outside function, we rewrite the inside function, and multiply through by the derivative of now the inside function. So let's go ahead and do that. So what we can say then is dy by dx, and this is doing it the manual way. So if I'm differentiating the outside function, I multiply down by the power, I rewrite the inside function, I drop the power by 1 and multiply through by the derivative of the inside function. The derivative of 3x minus 4 is 3. So we end up now with dy by dx will be equal now to 3/2, and then we have this value of 3x minus 4 to the minus 1/2. And again, you can write it exactly like so. In an exam, unless told otherwise, you can simply quote this. If you're using the chain rule, you can say by the chain rule, so by the chain rule, we end up now with this scenario. The chain rule will appear in so many different applications when you're working in calculus or working with calculus, but we're actually going to dedicate specific videos to both trig and exponential and log functions. What we will do in the video though is look at some basic examples of functions when we're dealing with both trig and exponential and log functions. So let's just recap now our standard results, and we looked at the standard results in the first video, so let's just go ahead and do those. So what we've got then, these are standard results for particular functions. So when we had y and we had now sine x, the derivative now dy by dx was cos x. If we had now y was equal to cos x, the derivative of cos x was minus sine x. And in the trig video, we will look at showing why this is the case. If we had now tan x, the derivative was sec squared x. And we can show this with something called the quotient rule, which again we will look at in a later video. If we had sec x, the derivative was sec x, and then we had tan x. If we had now cot x, so cotangent x, we had minus cosec squared x. And if we had cosec x, then we had now minus cosec x, and then we had cot x. Then we looked at, so these were our trig standard results, and we'll build on these as we go. Then we had the exponential. If y was equal to e to the x, the derivative was also e to the x. And that was one of the key features of the exponential function, which we spent some time looking at. And then if we had the natural log of x, the derivative was 1 over x. So there we go. That gives us now our basic list of our standard results. So let's go ahead and look at some functions of functions using these. And I'll just rule off a bit down here and we'll work with these. So what we're going to now do is look at particular functions of functions. So let's say we had now, for example, y is equal to sine of 2x. So we got sine of 2x. This is a composite function or a function of a function. The inside function is 2x. The outside function is sine x. So what we could say then is let u be equal to the inside function of 2x. Therefore now we've got y is equal to the sine of u. We could use the chain rule now to differentiate this function of a function. So what we'd have then, dy by dx would be equal to dy by du. So the derivative of y with respect to u is just going to be cos u, and then we'd multiply this by by du dx. Now, if we've got u is equal to 2x, then the derivative now is simply going to be 2. So we could say now that dy by dx was equal to 2 cos u. We could say now, but u is equal to 2x, and we end up now with dy by dx being equal to 2 cos 2x. We will look at, again, a more informal approach. But essentially, if we have now y is equal to now the sine of kx, where k is a constant, then the derivative dy by dx will be equal to k cos kx. In the same way, if we had y is equal to cos of kx, it would be minus k sine kx. And again, we could have any function in here. I've just put the sine of 2x. We might have the sine of 2x squared plus 3x plus 4. We would just simply differentiate that inside function and then multiply through once we've differentiated the outside function. So that's the formal way. Again, you wouldn't be expected to show this. So let's say now we have y is equal to, let's say we've got 3 cos now of, let's go for x squared. So this isn't cos squared x, it's cos of x squared. So what we want to do is find the derivative. So what we're going to have then, and I will do this informally, we've got now dy by dx. We're going to differentiate the outside function. Differentiating minus 3 cos x, differentiating 3 cos x will give us minus 3 sine. We rewrite the inside function and multiply through by the derivative of the inside function. So we end up now with dy by dx equal to minus 6x sine of x squared. If you wanted to go for the formal approach, you could let u be equal to x squared. So let's take it back here. Let's just take it to this stage right here. So all I've done is simply differentiated the outside function. The outside function is 3 lots of cos of x. The derivative of 3 cos x is minus 3 sine x. We've left the inside function alone and multiplied through by the derivative. So let's say now, if y is equal to cos of 3 cos of x squared, let u be equal to x squared. We know by the chain rule that dy by dx will be equal to dy by du multiplied now by du dx. So if we look now at the derivative, and we can write this here, so what we've got then is y is equal to now, and we've got u just here, so we've got now 3 cos of u. So we've got 3 cos of u, because u is x squared. So if I differentiate 3 cos of u, dy du, so dy du will be equal to minus 3 sine u. Okay, so all we've got to do now is multiply that by du dx. Now, if we think about u is x squared, so multiplying by the derivative, that's going to be 2x. So I'm just differentiating u with respect to x. So all we've got to do is multiply these two by the chain rule. That's these parts right here. So we can say that dy by dx will be equal to minus 6x sine u. We know that u is equal to the x squared, so we can say that dy by dx will be equal to minus 6x, and then we got sine of x squared. So all I've done is simply now gone ahead and done exactly the same. We've done now the formal and the informal approach. As stated earlier, we will now look at an in-depth video on trig functions and differentiating a whole range of them. Okay, let's look now at some exponential ones. So let's say we've got now, let's say y is equal to e to the x squared plus 3x plus 1. So what we have here is a function of a function. So what we're going to say is let u be equal to this inside function. So if we say let u be equal to x squared plus 3x plus 1, we've got y is equal to e to the u. If we look at the derivative now of e to the x, we get e to the x. So the derivative of e to the u is this e to the u. So we can say that dy by by du is equal to e to the u, we can say from here that du dx, so let's write du dx is going to be now the derivative of x squared plus 3x plus 1, which is going to give me 2x plus 3. So by the chain rule, what we can say now, and we'll just write it here, dy by dx will be equal to the quantity 2x plus 3 multiplied by e to the u. But we know that e to the u, now with u being equal to the quantity here, x squared plus 3x plus 1, we could say that dy by dx will be equal now to 2x plus 3 multiplied now by e to the power of x squared plus 3x plus now the 1. And that's all it is. I would much prefer to do this informally and look at it as a very algorithmic process. So we differentiate the outside function, we then rewrite the inside function and multiply through by the derivative of the inside function. So if we pick this up again, we've got now e to the power of x squared plus 3x. So we would then have now differentiating the outside function is just going to give us now e to the x. So we'd have now e to the x squared plus 3x plus 1 multiplied by the derivative, which is going to be the quantity 2x plus 3. When we're differentiating e to the x, we get e to the x, and it might be a little strange, but essentially when you're differentiating that exponential function, you're simply multiplying by the derivative, because when you differentiate e to the x, you get e to the x. Okay, let's finish with a couple more. Let's look at, let's say we had now y is equal to 2 lots of the natural log of, let's go for x squared plus, let's say, let's go for 2x plus 1. Okay, so what we have now is a log function. We've seen that the derivative of the natural log of x is 1 over x. So what we're going to do is differentiate the outside function, rewrite the inside function, and multiply through by the derivative of the inside function. If you want to, though, first look at this in a very formal way, we can let u, so let u be equal to the inside function. So we've got now 2 lots of the natural log of this inside function. So we've got x squared plus 2x plus 1. So if we look now, we've got y is equal to 2 lots of the natural log of u. The derivative of the natural log of u is 1 over u. So what we can say then is dy by du will be equal to 2 lots of 1 over u, or you could say 2 over u. So all we're going to do now is multiply this by du dx. So we've got du dx, and that's going to be now 2x plus 2. Or we could write now, if we wanted, to the quantity x plus 1. So 2x plus 2, derivative of that. I'll just write it here, let's write it here. Du dx is equal to 2x plus 2. So what we end up with then is the following. If we put these two together, remember that dy by dx is dy by du multiplied by du dx. So dy by dx will be equal now to 4, and then we're going to have the quantity x plus 1, and then we're going to multiply this by 1 over u. So just multiply these, but we know that u is equal to x squared plus 2x plus 1. So writing this here, but now u is equal to x squared plus 2x plus 1. So we can write at this stage now the following. So dy by dx in terms of x, instead of in terms of x and u, we got 4 lots of x plus 1, and then that's going to be over now the u, which is going to be x squared plus 2x plus 1. So that is the formal approach. The informal approach is to now differentiate. And the way I like to think about this now is we write the following. We write 2 lots. Now, I'm going to write 1 over the inside function. So I know that the derivative now of the natural log of x is 1 over x. So we're going to have now 1 over the inside function, which is going to be x squared plus 2x plus 1, multiplied through by the derivative of the inside function, which is going to be this 2x plus 2, or we're going to have 2 lots of x plus 1. So you can see that we're going to end up with exactly the same. So when we're differentiating a log function, we write 1 over the inside function and we multiply through by the derivative of the inside function. So for example, now if we have the natural log of 2x, the derivative, so let's just look at this, the derivative with respect to x, 1 over the inside function multiplied through by the derivative of the inside function. So you can see if you have now the natural log of kx, the derivative will still be 1 over x, as those, now the derivative here is going to cancel. If we had now the derivative, let's look at this, derivative with respect to x of, let's say we got 5, the natural log of x cubed minus, let's say minus 2x plus 4. We're going to write 1 over the inside function. So let's just write here, let's write that's 1 over the inside function, which is going to give us now x cubed. So we're going to have x cubed minus 2x plus 4. So we've got 5 lots of this. And then we're going to now multiply through by the derivative of the inside function, which is 3x squared minus 2. So we'd end up with now 5 lots of 3x squared minus 2 all over now x cubed minus 2x plus 4. And that is the informal approach. So there we go, that's a chain rule. That's a whistle-stop tour. In later videos we will look to bring all of these rules together. So we're going to introduce the quotient rule and the product rule, and many of these functions of functions are also part of what we would call a product or a quotient. So in the videos we will look at some specific trig and exponential and log derivatives. But for now, hopefully that's made some sort of sense. The idea of a chain rule is that we have a function of a function, or we have multiple composed functions. So we might have h of g of x, so we've got 3 functions. And essentially what we're doing is making a substitution, and we can state that dy by dx is dy by du multiplied by du dx. And whilst they're not fractions, they're limits of fractions, we see now that the du's cancel, and we can multiply now the 2 results. You can make the substitution back for u is a function of x, or you could just simply now do it in this very mechanical process of differentiating the outside function, rewriting the inside function, and multiplying through by the derivative of the inside function. As long as you're putting by the chain rule in an exam, you will not be penalised. So there we go, introduction to the chain rule, and in the next video we will look at the product or the quotient rule.